Welcome to Month 5 of the Senior Engineer track. This session is titled Technical Leadership, and it covers the skills that separate a senior engineer who is individually excellent from one who makes the whole team better. Over 4 hours, you will work through code reviews, mentoring approaches, team coding standards, and technical decision-making. These are not soft skills. They are the core practices that determine whether your team ships quality software at pace or grinds to a halt in review backlogs, tech debt, and misaligned decisions. Here is how the 4 hours are structured. Hour 1 is Code Review Excellence, Best Practices, a workshop where you review sample pull requests, and a discussion of common anti-patterns. Hour 2 is Technical Standards, how to create team guidelines that actually get followed, how to automate what machines can check, and when to enforce versus enable. Hour 3 is Mentoring Practice, 4 approaches matched to different situations, followed by role-play scenarios covering the most common difficult mentoring conversations. Hour 4 is Technical Leadership, Decision-Making Frameworks, presenting refactoring plans, and the offline milestones for Month 6. 5 things you will be able to do by the end of today. First, conduct effective code reviews across all 6 dimensions: correctness, design, readability, maintainability, performance, and security. Second, create team coding standards that are specific, automatable, and useful rather than a document that nobody reads. Third, mentor junior developers using techniques matched to their actual situation. Fourth, make and document technical decisions in a way that creates a record future engineers can learn from. And fifth, lead design reviews that produce better decisions rather than just consuming everyone's time. A code review has 6 dimensions, and most reviewers default to 1 or 2. Correctness asks, does it work? Are edge cases handled? Check logic, boundary conditions, and error paths, not just the happy path. Design asks, is it well structured? Does the change fit the existing architecture or introduce accidental complexity? Readability asks, can another engineer understand this in 6 months? Naming, abstraction level, and comments all matter here. Maintainability asks, is it easy to change? A working solution that is hard to modify becomes tomorrow's tech debt. Performance asks, are there obvious bottlenecks? An N+1 query in a loop that runs once per page load is a different severity to one in a batch job over 1 million rows. And security asks, does this introduce vulnerabilities? Injection, authentication bypass, data exposure, and missing input validation are the most common. Reviewing across all 6 dimensions consistently is what makes you a senior reviewer rather than a style checker. There are 4 anti-patterns that make code reviews painful or ineffective. The first is nitpicker syndrome, leaving 15 comments about naming conventions and camel case while missing the N+1 query that will take down production. Style feedback belongs in linters and formatters, not review comments. The second is drive-by approval, typing LGTM after 30 seconds on a 400-line pull request. You are not reviewing, you are adding your name to the commit history without taking any accountability for the outcome. The third is delayed reviewing, sitting on a pull request for 3 days, and then requesting major changes that could have been caught on day 1. The fourth is vague feedback. This is confusing, with no explanation of what specifically is confusing or how to improve it. Good feedback quotes the specific line, names the problem, and proposes a solution or asks a clarifying question. The most reliable feedback structure for code reviews is the SBI model: situation, behavior, impact. Situation is the specific context, not a generalization. Name the pull request, the file, the line number. Vague feedback triggers defensiveness because the recipient cannot tell what specifically to change. Behavior is the observable action, what the code actually does, not what you assume the intent was. Impact is the effect of that behavior on the system, the team, or the user. A complete SBI comment sounds like this. In the authentication PR, at line 83 of user's service dots, the password is logged to console, which means if these logs are ever shipped to a log aggregation service, user credentials will be exposed in plain text. The situation grounds it, the behavior is specific and observable, and the impact makes clear why it matters. This structure works for praise as well as correction, and it teaches rather than just instructs. Here is the SBI model applied to a real code review comment. The code under review is an async function that queries all users from the database and then, inside a for loop over those users, runs a second query to fetch each user's orders. This is a classic N+1 problem. A weak comment says, "This is slow." A strong comment says, at line 83 of user's service, dots, the current implementation runs one database query per user to fetch orders. On a table with 10,000 users, that means 10,001 queries per request. Consider fetching all orders in a single query with a where user (in) clause and joining them in memory, or using a join if orders are always needed with users. The strong comment names the exact location, explains the mechanism of the problem, quantifies the impact, and proposes a concrete fix. The developer can act on it immediately without a follow-up conversation. The first rule of team coding standards is to automate everything style-related. If ESLint, prettier, or a pre-commit hook can check it, humans should not spend review cycles on it. Style debates in review comments waste time and create friction. Enforce them at commit time instead. The second rule is that standards should be prescriptive at the boundary and flexible in the implementation. Mandate error handling patterns and logging format. Do not mandate how someone names a private variable inside a 10-line function. The third rule is that standards exist to enable, not to police. A standard that makes engineers faster and more confident is worth keeping. A standard that requires manual interpretation and generates arguments is worth questioning. Review your team's standards every quarter. Which ones are being enforced by tools? Which ones are generating the most review comments? And which ones nobody follows in practice? The ones in the last category are not standards, they are aspirations. Pull request size has a direct and measurable impact on review quality. Small pull requests, under 100 lines, should be reviewed the same day, and they receive the deepest, most useful feedback. Medium pull requests, 100 to 300 lines, are the sweet spot for standard feature work and should have a 1 to 2 day SLA. Large pull requests, over 300 lines, get shallower reviews because reviewers lose context, and the review SLA extends to 2 to 3 days. Above 500 lines, review quality drops sharply and approval often becomes a formality. The practical implication is that breaking work into smaller, reviewable units is a skill as important as writing the code itself. If you find yourself consistently submitting large pull requests, examine whether the feature decomposition happened at the planning stage. A pull request that takes 3 days to review and blocks multiple people is a delivery bottleneck, not a sign of thorough engineering. Effective mentoring uses different approaches depending on the situation. The 4 are teaching, coaching, supporting, and delegating. You teach when someone has never seen a pattern before, explain the concept, demonstrate with a real example, then watch them apply it. You use pairing here. You coach when someone is stuck but has the underlying capability. Ask guiding questions rather than giving the answer. What have you tried? And what does the error message tell you? develop problem-solving skills. It's on line 42, does not. You support when someone needs confidence, not information. They know what to do but doubt themselves. Validate their thinking, point to evidence of their competence, and reduce the noise so they can execute. You delegate when someone is ready to grow. Give them ownership of a real problem with real consequences. Make yourself available as a resource, but do not hover. Matching the approach to the situation is the core skill. Overteaching someone who needs coaching creates dependency. Under-coaching someone who is genuinely stuck wastes their time and yours. 3 scenarios come up repeatedly in senior engineering roles. The first is the defensive developer, a junior engineer who pushes back on every review comment and takes feedback personally. The right approach combines coaching and support. Acknowledge what is working first. Find something genuine to praise before raising the issue. Frame feedback around the impact on the system, not the engineer's ability. Ask, "What do you think about this approach?" before stating your view. The second is the silent struggler, a team member who is clearly stuck but will not ask for help. Create a low-stakes opening. "I noticed you've been working on that function for a while. Want a rubber duck session?" Normalize asking for help by doing it publicly yourself. The third is the over-engineer, a developer who adds unnecessary abstractions, builds for hypothetical future requirements, and makes simple problems complex. The most effective question is, "What's the simplest thing that could work here?" Followed by, "What specific future requirement are you designing for?" Requiring them to name the requirement usually resolves it. A technical decision record, or TDR, is a short document that captures what was decided, why it was decided, and what alternatives were considered. The canonical template has 5 sections: context, which explains why the decision was needed and what forces were at play; decision, which states what was chosen, 1 clear sentence; alternatives considered, which lists what else was evaluated and why it was not chosen; consequences, which covers the positive and negative implications of the decision; and status, which is proposed, accepted, or deprecated. TDRs are valuable not because they prevent bad decisions. They do not, but because they create institutional memory. 6 months from now, when a new engineer asks, "Why are we using Kafka here?" the answer is in a document rather than locked in the heads of 2 people who may have left the company. They also expose lazy decisions. If you cannot write down why you chose something over the alternatives, that is a signal that the decision deserves more thought. Here is what a TDR looks like filled in. TDR 12. Use PostgreSQL over MongoDB. Context. A new reporting module needs to store user activity events. The team proposed MongoDB for its schema flexibility, but the events have a consistent structure, and the reporting queries are relational joins across users, sessions, and events. Decision. Use PostgreSQL with a JSON column for event metadata. Alternatives considered. MongoDB rejected because the team has strong PostgreSQL expertise, and the query patterns are relational, not document-oriented. The JSON column gives sufficient schema flexibility without adding a second database technology to the stack. DynamoDB rejected because it optimizes for single-item access patterns. Our reporting queries scan ranges and aggregate across multiple users. Consequences, positive, 1 database to operate, consistent with existing tooling, strong query planner for analytics. Negative, JSON columns are less ergonomic than native document storage for deeply nested structures. Status, accepted. Notice that the document is short. A TDR does not need to be thorough to be useful. It needs to record the decision and the key reason for it. Technical decisions made well follow a consistent pattern. The first step is framing the problem correctly, not the solution. Should we use Redis or memcached? Is a solution frame. What catching behavior does this feature need? Is a problem frame. The second step is enumerating real alternatives, not the obvious choice plus 2 strawmen. If all 3 options you evaluate are variations of the same approach, you have not actually explored the decision space. The third step is identifying the decision criteria before evaluating the options, not after. Deciding that latency matters most, then comparing options on latency, is sound. Evaluating all options, and then noticing that the one you preferred also has the best latency is motivated reasoning. The fourth step is acknowledging what you do not know and building in a trigger to revisit. We will use this approach until query volume exceeds 10,000 per second, at which point we will revisit is a better decision than one that assumes current conditions persist indefinitely. A design review meeting should produce better decisions, not just consume time. There are 4 practices that determine whether it does. The first is preparation. Circulate a 1-page design document 24 hours in advance. The meeting is for questions and trade-offs, not for the presenter to read slides aloud to a room that has not seen them. The second is having a clear problem statement in the document, not just a proposed solution. Reviewers cannot evaluate a solution if they do not understand what problem it solves. The third is time-boxing the Q&A and separating clarifying questions from design critique. Let everyone ask clarifying questions first, then open the floor to alternatives and trade-offs. The fourth is capturing decisions and open questions explicitly. End the meeting with a decision log. What was decided, who made it, and what is still unresolved. A design review that ends with, "We'll follow up offline" on every open question is a meeting that should have been a document. The Month 5 challenge is 3 hours of technical leadership in practice. Your scenario: you are the tech lead for a team of 2 mid-level and 2 junior developers. The codebase has significant technical debt, and you have a new feature to deliver in 2 weeks. You will produce 4 deliverables: a code review report on a junior engineer's pull request, a code review report on a mid-level engineer's pull request, a team code review guidelines document, and a technical decision record for a specific architectural decision you need to make. The challenge is designed so that doing it well requires using the SBI modal, the 6 review dimensions, the TDR template, and at least one of the 4 mentoring approaches. You have the sample pull requests and the decision context in the challenge brief. Read them before the clock starts. 4 submission files. Name them exactly as specified. Your name, then month 5. Then the deliverable slug. Review 1 for the junior PR. Review 2 for the mid-level PR, guidelines for the team standards document, and TDR for the technical decision record. The assessment criteria weight each deliverable at 25 points, and passing is 75 out of 100. Before month 6, there are 5 offline milestones. Conduct a live code review session with your actual team and capture the outcomes. Introduce at least 1 new team standard with automated enforcement. Write 3 TDRs for real decisions your team has made or is making. Run 1 formal design review and write up the decision log. And read Camille Fournier's The Manager's Path, chapters 1 through 3. It is the most practical account of the senior engineer to tech lead transition, written by someone who has done it. Technical leadership is not a title you earn once and carry forever. It is a practice, something you get better at through repetition and reflection. You do not become a technical leader by writing more code. You become one by making the whole team more effective. Code reviews teach. Standards enable. Mentoring multiplies. Decisions compound. That is the work of month 5. and the foundation for everything in month 6.